And over there on the side, I want to draw again this idea of thermodynamics is watching something invisible. It's watching the flow of energy. So we talked a lot about this idea where you could have a system where you have a chunk of block. This could be some sort of metal. Okay. This is our system within the beaker. Here's some chunk of block. In this case, let's make sure I do this right. I think last time I was talking about endothermic. And actually, if we made the water hot, we could actually be heating up our metal like that. In this case, our metal is having energy added to it, so it's endothermic. In this case, we can make our metal hot and our water cooler, and energy would flow that way. And we would call this, with regard to the metal block, exothermic. Well, what if, instead of that metal block, what if I had a chemical reaction going on? And I printed off something from part 5, where actually we were looking at hydrogen gas combining with oxygen to form water. I'll go ahead and for now just kind of disregard the physical phases. I think these are all three in their gaseous physical phase. To balance this, I'm going to put a stoichiometric coefficient of 2 there, and then to balance it, I need to put a 2 there. And if you look back in your notes for part 4, the heat of this reaction actually, was a whopping negative 483.6 kilojoules, according to that balanced chemical equation. So here's my question. What did we say? Is this endo? How many people think this is endothermic? How many people think this is exothermic? I do too. So all we're going to do is change it up, and we're actually going to call this our reservoir. It's French. And we're going to let that chemical reaction occur right here. So that's going to be our thing that within our system is going to create heat. How much heat? Well, according to the heat of the reaction. Where's that heat going to go? Well, it's going to go to what's surrounding. It's still the same system because my system is this. Everything in the dotted line is my system. Okay, so I have two things in there. I have the reservoir, which is actually also the RXN, the chemical reaction, creating the heat. Okay, and we're gonna, if we had a thermometer in that water, the temperature would go up. So actually, I'm kind of getting a little ahead of myself, but I'm gonna just go ahead and call this the Q, the system. Two things going on. We have a change in thermal energy of the created by the reaction, RXN. Sometimes this is called reservoir. And then we also have, I think in response to that, a change in thermal energy. I'm just going to call it SOLN. SOLN, that's like my water, my solution. And if it's isolated, the change in thermal energy of the system is equal to what? Then I thought, well, what the heck? Let's go ahead, and we talked about this. If I were to go ahead and change this up and now do the decomposition of water, take 2 moles of H2O in its gaseous state, decompose it into 2 moles of hydrogen gas plus 1 mole of oxygen gas, what would the heat of that reaction be? Yeah, it would be positive 483.6 kilojoules. And so, how many people think that's endothermic? So I could have this going on here. What would happen to the temperature of my water?
Decrease.
It would decrease. It would get colder. So we have the same thing. This actually is acting as a reservoir. I can call it Q of the reaction, or Q of the reservoir. I can say the other thing that's in the system is the Q of the solution. Now just know that the Q of the solution is kind of the matrix. It's kind of the amniotic fluid that the thing's happening in. And that's the only two things that are changing thermal energy in my system. And if it's isolated, that's equal to 0. So that's all this sort of problem is looking at. Okay. So in these types of problems, we are looking at a chemical reaction being endothermic or exothermic, and we're looking at the response, if you want to think of it that way, that the solution does. Okay. Notice that in italics and blue there, this, just like Hess's law, it doesn't have to occur stepwise like this, but we can kind of think of it as occurring kind of isolated, but it doesn't have to be isolated or a particular step. So I was talking about an energy reservoir. An energy reservoir is something that on its own will liberate energy, or something on its own that will suck in energy. And as I've described it, our reservoir over here were chemical reactions. So if the chemical reaction is exothermic, like right here, okay, then energy is released from the reservoir, which is a chemical reaction itself, and the solution's temperature increases. If the chemical reaction is endothermic, like the decomposition of water, then actually we're going to see our solution cool down. That's it. That's it. In a nutshell. And if the system is isolated with regard to matter and energy not crossing that barrier that is isolating the system from the environment or the surroundings, then the overall change in thermal energy of the system itself is 0. Okay. And so then we can go ahead and say that the change in thermal energy of the solution, which is the water, which is the matrix, plus the change in thermal energy associated with the reservoir happening within the system is 0 because it's isolated and closed. So here's where I kind of make that leap that I was kind of telling you about. In this case, and it's not always the case, but in this case, our reservoir is actually a chemical reaction. It's either an exothermic chemical reaction like hydrogen and oxygen combining to form water. That's exothermic, or it's an endothermic chemical reaction where water is actually requiring energy to decompose into hydrogen and oxygen. So you know what's coming next. We can rearrange this then, and since we only have 2 terms, which I can't remember, it's been a while since I've done the homework that you guys are turning in, but you don't always have 2 terms. Actually on Friday we're going to be talking about actually where you have multiple changes in thermal energy happening within your system, and it's all equal to 0. In this case, we have 2 things, so actually they are what? Equal in magnitude but opposite in sign. Equal magnitude but opposite in sign. And as you do these problems, you really cannot blow off the step, okay, for a number of reasons. So let's work a problem. I think I'll go ahead and diagram this here. Here's my famous beaker. I told my daughter the other day, your mom's the worst drawer of beakers. Okay, so we're gonna put 5.00 grams of magnesium in a coffee cup calorimeter. So, it should be my beaker. I'm gonna turn that into a coffee cup. I put my little thing on top here. So now I have just turned it into a coffee cup. So it's isolated. Already in that coffee cup, we have 100 with 4 sig figs milliliter of HCl that is at a molarity of 1.00 molar HCl. Now I'm going to go ahead and jot down, remember rho is the sign for what? Density. Yep, I'm going to go ahead and write down the density of the solution. And I'm going to put it as a little bit over the density of regular water. Instead of 1.00, it's 1.02 grams of solution, HCl solution, per 1 milliliter of solution. You can't go wrong unpacking things. Okay, do this. All right. It goes ahead and it says this reaction is going to let loose, where we have 1 mole of magnesium is going to react with 2 moles of HCl from our, this is where the HCl is coming from, to form hydrogen gas. So do you think the gas can escape like the things you used yesterday? You weren't here, but what do you guys think? Can H2 escape? Yeah, you actually had 2 holes here. So yep, it's not isolated with regard to material. So yep, it can escape, and it's going to form 1 mole of magnesium chloride salt. Oops. Cool. Well, that's all well and dandy. Now, I'll go ahead and tell you, and actually maybe I'll just show you the rest of the problem. It says we have a thermometer in here. Here's my thermometer. And it said the resulting solution's temperature was observed to increase from, so my T sub I, I'll put my little mark here, T sub I of the solution is 22.2 degrees Celsius. T sub F of the solution is 44.8 degrees Celsius. So what do you think? How many people think that this was an endothermic reaction between magnesium and HCl? How many people think it must have been an exothermic reaction between magnesium and HCl? Very good, you're right. It says calculate the enthalpy change. What's the symbol for enthalpy? H, yep. So I'm going to put a semicolon, question mark, enthalpy change, yep, delta H, for this reaction. We need to read it carefully. We're supposed to calculate the enthalpy change in kilojoules per mole of magnesium reacted. So my units here, and you're going to see why that's important, my units here are going to be kilojoules of energy per mole of magnesium. That's no small thing. Well, yeah, our H2 gas, if this is a simple cup calorimeter, that hydrogen gas is out of there. Okay. We are, though, going to assume that as it leaves, it doesn't carry away a significant amount of energy in its cute little gas particles. Okay. We're also going to assume that, and this is not a small thing, I'm going to add it to the diagram here. Also assume that the resulting solution's specific heat is the same as that of water, the solvent. Now this might, as I'm thinking about today, this afternoon, I'm like, well, you're like, well, the density of the solution is different than that of water. Okay, but we're going with the specific heat is the same of water. So I'm going to go ahead and put that on my diagram. If you run onto a test, you need to dissect all the information given. If the specific heat of this is the same as water, what is the specific heat of this? Yep, 4.184 joules per gram degrees Celsius. If you've been doing calorimeter problems, that's probably ingrained in your mind. Yep. So before I do my slides, let me kind of pencil in how this is going to work. So over there, I said we're going to use this relationship. Q of the system has 2 things going on. We have a change in thermal energy, Q related with the reaction, that's exothermic. And we have kind of a response to that, a change in thermal energy of our solution, or kind of our matrix sort of thing. And that's equal to 0. So you can simply arrange that, and we can say Q of the reaction is equal to negative Q of the solution. Now, and I don't know, you just need to do a gads of these, gads meaning a lot of them, in order for you to pick this up, but hopefully you can pick this up, that we can get to the Q of the solution simply by applying that thing that seems like it's got a good rhythm. Q is equal to M, C sub P, delta T. If we can get to the Q of the solution, then Q of the reaction is negative Q of the solution. So just looking at here, what do you think? Well, I'll go ahead and kind of answer my own question. The mass term, actually, we can get from volume and density. Does that make sense? Volume and density, you knock out mass. The specific heat, down here in the end, it said we're using the same specific heat as that of water. Our delta T, we have our delta T over here, and delta T is always final minus initial. So we have all three of those terms to get to the Q of the solution, and then the Q of the reaction is negative Q solution. Oh, but I forgot this. Okay. So I told you to get to the mass of the solution, we can use this volume and the density of the solution to get to grams. But notice what I forgot is we have to consider also the mass of the magnesium that was added. So here in a minute, when I go for the mass of the solution, you're going to see me use volume and density to get mass of solution, and I'm going to tag on my 5 grams. The specific heat, like I said, that we're going to use of the solution, our instructions were to use the 4.184 joules per gram degrees Celsius, the same as that of regular water. And the delta T, let's go ahead and knock that out. Deltas are always final minus initial. In this case, the final temperature, we were given 44.8 degrees Celsius minus the initial temperature, 22.2 degrees Celsius. Since we're subtracting, we round according to decimals, so you're looking at delta T of 22.6 degrees Celsius. I might have mentioned this before, but there's this cool thing in working physical science problems is that if you're adding or subtracting, which we are here, and if our units are the same, we can actually just kind of put our numbers, and then outside of our numbers that we're adding or subtracting, put the units. It's not cheating. All right. So then the next step is to go ahead and plug those, the mass, the specific heat, and the delta T in. Oh, sorry, we don't have the mass yet. So the mass of the solution, I said we had to account for the mass of your HCl and the mass of your 5 grams of magnesium. So we're simply going to take the volume, we're going to take the non-flipped version of the density, 1.02 grams of solution for 1 milliliter solution, round it to 3 significant figures, and you're looking at 100.2, sorry, you're looking at 102 grams of solution. And related to the conservation of mass, I know that this mass over here, these two masses should be the same, albeit we lose some mass with our hydrogen. But I need to include the mass of the magnesium. So if I take 102, which is the mass of the HCl, plus, oh goodness, I put the wrong number here. Must have put the wrong number here. Instead of 5.00 grams, sorry, 0.500 grams. Oh, yep. Okay. Now, an interesting thing happens here. I don't know how interesting it is, you guys think it is, but notice that we're adding, so we have to round according to decimals. This first term has no decimals. This second term, the mass of magnesium, has 3 decimals. So we round according to no decimals, which our calculator would display 102.5, which 102.5 rounded up to no decimals is 103. So that's where that number comes from. Okay, so Q is equal to M, C sub B, delta T. And again, when you work this, I'm going to be looking for your units. It's not a plug and chug sort of thing. So 103 grams, I usually put that over 1. C sub P is 4.184 joules per gram degree Celsius. And the delta T we had was 22.6 degrees Celsius. So if I put the first and the last term over 1, which I like to do, notice now that our units of grams cancel, our units of degrees Celsius cancel, we're left with units of energy, which is perfect. I can't remember if I convert this now from joules to kilojoules or not. Yes, I do. I'm going to go ahead and introduce one more term, just so my number isn't so big. I'm going to go for kilojoules instead of joules. So we have exact relationship. 1 kilojoule is exactly equal to 1,000 joules. So now units of joules cancel. I'm left with units of kilojoules. How many sig figs? 3. I'm liking it. Yeah. So 9.74 kilojoules of energy. And you might be patting yourself on the back because you got Q, you got that energy that was released, and you should pat yourself on the back. But a few things we need to clean up. First of them is we need to go and make sure we apply this. That's your Q of the solution. So Q of the reaction is equal to negative that. Okay? Q of the reaction is equal to negative Q solution. In other words, Q reaction is equal to negative 9.74 kilojoules. Which makes sense because you guys told me it was exothermic because the water heated up. Then you might be thinking, well, I've got to be done now. And there's 2 more loose ends on this problem. One of them, and we're going to do this secondly, one of them is we need to, it's called normalization. This is the amount of energy released for the whole thing. Actually, this is the amount of energy released for 0.500 grams of magnesium. We want it normalized on energy per mole of magnesium, so we're going to have to fix that. One thing I don't like about this example problem is not only that, but we need to convince ourselves, you know, we have 2 reactants, reactant 1, reactant 2. We need to convince ourselves which reactant was the limited supply. If you're like me, your intuition would say, well, dang, I bet the HCl was in excess with this 100 milliliters. I bet that was way in excess and all of your magnesium was used up. Actually, you're right, but you can't assume that. On a test for this sort of problem, I wouldn't, I think in homework I do make you do this, but on a test, I wouldn't make you do that. So, but that's the next step we're going to do, is we're going to convince ourselves that we had HCl in excess and magnesium was limited. So we're pulling in something from Unit 2 in this class that you guys talked about, or I talked about. So if we're going to try to see which one we ran out of first, so under the magnesium, I'm going to put 0.500 grams, and under the HCl, I'm going to put 100 milliliters of 1.00 molar. So I got to see which one I ran out of first. So I'm going to do the half moles and then the need moles approach. So the molar mass of magnesium, I love that phrase, is 24.31 grams per mole. So we're going to use the flipped version of the molar mass, 1 mole of magnesium for 24.31 grams of magnesium. So then the half moles to 3 sig figs is 0.0206 moles of magnesium. We've talked about how you can use solution volume and concentration to get to moles. That's what we're going to do with the HCl. We had 100 milliliters, so 100.0 milliliters of solution. But we got to get from milliliters to liters because molarity is in liters. So the next term is going to be 1 liter of solution over 1,000 milliliters. And now finally we can introduce molarity. There's a lot of ones and zeros here. Our molarity is 1.00 moles of HCl per 1 liter of solution. Wow, there's a lot of, let things kind of cancel how they're going to. And you end up with 0.100 moles of HCl was what we had. So again, this is the sort of calculation we did back in Unit 2. So these are our half moles. So I'm going to take a ratio of those half moles. I'm going to compare it to a ratio of the need moles from the stoichiometry. So from the stoichiometry, we need 2 moles of HCl for every 1 mole of magnesium. 2 moles of HCl for every 1 mole of magnesium. Divide that out, you get 2. So our need ratio is 2 moles per 1 mole. The have ratio from the previous slide is we have 0.100 moles of HCl and we have 0.0206 moles of magnesium. If you divide that out and give yourself 3 sig figs, you get what you have is 4.185 moles of HCl for every 1 mole of magnesium. So you can see that with regard to HCl, we have more than we need with regard to HCl. Goodness. Okay, so is HCl, how many people think that HCl is in excess? Yep, HCl is in excess. Phew. And again, that's kind of like a little side calculation, but theoretically, or not theoretically, we just needed to do that. So since magnesium is in limited supply, it will entirely be reacted up. And so now finally we can go ahead and normalize that Q of our reaction. Now we're ready to go ahead and finish the problem. And it looks like this. So the Q of the reaction we had was at negative 9.74 kilojoules. We want kilojoules per mole of magnesium. And on our way to that, we're just going to take that kilojoules and divide it by that 0.500 grams of magnesium. So what's one more ratio that we can do to clean it up to get us to energy per mole? How can we get, sorry, it is energy. You're looking at me like, this is nice. All right, we had that number before, so we don't have to go ahead and, I was going to reinvent the wheel. So this will give us where we want to go. 3 sig figs, right? Dun, dun, dun. So the heat of the reaction is negative, now this would be the normalized, negative 473 kilojoules of energy. And we have been talking about heats of reaction are always given for a balanced chemical equation. And this balanced chemical equation has 1 mole of magnesium. So it's perfect. That's it. Voila. I'm going to take a quick picture of this just because I figured out how to do it on my Surface Pro. A picture of this. And I'll go ahead and put it on the Twitter feed in addition to today's recording. Okay? So that's all I have.
So the knot is just for standard conditions, right?
The knot is just for standard conditions, yeah?
That's what it is.
That has. Right. Okay.
You had 3 dots, and I don't know what they are.
Oh, okay.
I'm not sure what they mean.
Anytime. Yep. Anytime on my solution you run into that means therefore.
Oh, okay.
Sorry.
Okay, so do I have to put that? Because I was like, I didn't know if I should or not.
No,
but
probably
I just
not.
rewrite, like, delta H not.
You could say that means, or if you don't even say that means, if you're working a problem and it's obvious that's the answer, that's fine.
I was like, I don't know if I should put the dots, so I erased them. I was like, that's not what I usually do.
Yeah, dots mean, the 3 dots mean therefore. So.